So those are the two deer moose models that we have just found the equilibrium points and the stability for. But I want to back up because I want to make a very big conceptual point. And in order to do that, I actually want to go back to one-dimensional systems. Now, you remember that equilibrium points in one dimension come in exactly two flavors, and they are stable equilibrium points and unstable equilibrium points. Those are the two equilibrium points that can occur in a 1D system. And you will recall that both of these are the solutions to differential equations. This first equilibrium point is the solution to the differential equation x prime equals minus kx. And the unstable equilibrium point is the solution to the differential equation x prime equals plus kx, where, of course, as usual, we're assuming k is bigger than 0. So the bottom line there is all equilibrium points are linear equilibrium points. And that's what we call the Hartman-Grobman theorem, that says that equilibrium points are always linear equilibrium points. And then the question was, what does nonlinearity do? And the answer is the thing that linear equations cannot do, which is have multiple equilibrium points. And in this case, for example, we looked at the logistic differential equation, which was, of course, x prime equals bx times 1 minus x over k. And when we graphed that vector field or differential equation, it looked like that. And the two equilibrium points are here and here. And as we saw, the principle of linearization tells us that here's the linear approximation there, here's the linear approximation here. This, if we draw state space now here, which is x space, then this equilibrium point is an unstable equilibrium point, and this equilibrium point is a stable equilibrium point. In other words, near this equilibrium point, this nonlinear system, notice the x squared, this nonlinear system here acts like this linear differential equation, and near this equilibrium point, it acts like that linear differential equation. So what does a nonlinear system do that a linear system can't do? Answer: have multiple equilibrium points that are going to be strung together by the nonlinear system. So now let's talk about two dimensions, like the deer-moose examples we were talking about before. We laid out what the linear equilibrium points in 2D are. I'll give you the zoo. We can have a purely stable, and that's stable, and the differential equation corresponding to this is, if this is x and y, is x prime equals minus k1x, y prime equals minus k2y. These are, of course, linear equations. You're just multiplying by a constant. The second example was the purely unstable, and that looks like this. And that is a solution to x prime equals plus k1x, y prime equals plus k2y. Then we talked about the saddle point. And the saddle point has an outgoing direction and an incoming direction. And that is, of course, a saddle point, which is unstable. It's classified as a form of unstable equilibrium point. And its differential equation is x prime equals k1x, y prime equals minus k2y. And that's a linear equation. And then we had the interesting ones that were not just mix and match. We had the pure center. We call it a center or a neutral equilibrium point. And that is exemplified by the differential equation x prime equals y, y prime equals minus x, which you notice is also a linear equation. We had the unstable spiral, which is exemplified by the differential equation x prime equals y, y prime equals minus x plus y. Again, all linear. And the third interesting equilibrium point was the stable spiral. And that's exemplified by the differential equation x prime equals y, y prime equals minus x minus y. And that is a linear equation. So these are the 6 kinds of linear equilibrium points. But by the Hartman-Grobman theorem, by the principle of linearization, we also know that these are the 6 equilibrium points that can occur in any differential equation, any nonlinear differential equation, because what the Hartman-Grobman theorem tells us is basically all equilibrium points are linear equilibrium points.